So the first question is, what are the different types of logic circuits? So the first type is the combinational logic circuit. It is usually used or implemented with only NAND and NOR because these gates are economic and easier to design. As you can see, this is a direct path from the input, three inputs to the output. You cannot see any feedback here. If there are changes in the input, it will also affect our output. As you can see from the truth table, we have different combinations of inputs, and for each combination, there is a corresponding unique output. So this is our input A, and this is B, and this is C. For combinational logic, the basic building block is logic gates. So every combinational logic, there is a certain logic gate present in your circuit. There are also three ways to specify the function of a combinational logic circuit. So this is the first example, which is the logic diagram. The second example for format is the truth table. And the third is the Boolean expression. The Boolean expression for this is A and B not, and plus the NOR gate, all with uh, not. And simplifying this is just A, B, and C not. This second type of logic circuit is the sequential logic circuit, and it has a feedback, or also known as memory. In this circuit, the feedback is D. This means that the output is being used as the input, meaning the output not only depends on the present input but also depends on the past input. The other circuit is what we call the flip-flop circuit. This flip-flop can be asynchronous or synchronous. This flip-flop is asynchronous, meaning there is no clock signal, while if the sequential logic circuit is synchronous, there is a clock signal in the circuit, and this clock signal is used to synchronize the memory element state. The difference between the two types of logic circuits is that the combinational has no feedback and the sequential has a feedback. Combinational circuits depend only on these inputs, but in sequential, they also depend in the past inputs. Sequential circuits require a clock, and combinational circuits doesn't have a clock. Also, sequential circuits has a memory, and combinational circuits does not. And as you can see from the logic diagram, the combinational circuits are direct and has only one path, and the sequential has different paths because there are feedbacks. And then combinational circuits are more easy to design, and sequential is complex to design. There are also different combinational logic circuits, and first is the half adder, where the outputs are sum and carry. If these are the inputs, A and B, the outputs are the S and C, or the sum and carry. For the sum, the relationship is just A not B plus A B naught, or this is equal to a NOR gate. And for the carry, the relationship is just A and B. If we draw the logic diagram of this A and B, there is an AND gate here for the carry. So the output here is C, and we have the NOR gate for the output S or the sum. The application of this half adder is just simply to add numbers. For example, we will add 0 plus 0, the answer is 0. 0 and 1, the answer is 1. 1 and 0, the answer is 1. 1 and 1, the answer is 0 with a carry of 1. If looking in the truth table, we have 0, 1, 1, and 0. We will not use the carry 1, so the sum is just 0, 1, 1, 0. And for the carry, the only pair that has a carry is the 1, 1 pair. So this is the 1, 1 pair and have the carry of 1. That is the half adder. The second type is the full adder, where we have three inputs, the A, B, and carry, and the two outputs, the sum and carry out. So the block diagram for the full adder, where we have three inputs, the A, B, and the carry, and the output is the sum and carry out. The logic circuit for this will consist of three AND gates, where the inputs are A, B, and then A and C carry, and B and C carry. And these three will go into our OR gate. This is the OR gate. So as you can see here, if we add 0, 0, the sum is 0 and the carry is 0. If we add 1 alone and the rest is 0, the sum is 1, the same is here with 0 carry. If we add two inputs with logic 1 and only one input with logic 0, the sum is 0 and carry is 1, the same here and here. But if the three inputs are 1, we have the sum of 1 and the carry out of also 1. So the application of full adder is obviously to add larger binary numbers because of the added third input, which is the carry, compared to our half adder that consists only of two inputs. The third one is the half subtractor, which is very similar to our half adder with the same input A and B, but the output is just difference and borrow. So they should be B and borrow. Let's see if we subtract 0 and 0, that is 0 and 0. If we subtract 0 and 1, that is automatic 1, because if we borrow to the next higher digit, the base is will become 2, and 2 minus 1 is 1. And 1 minus 0 is 1, 1 minus 1 is 0. So this half subtractor is used to subtract two binary numbers. The fourth one is the full subtractor, where we have three inputs and two outputs. The inputs are A, B, and borrow, and the outputs are difference and borrow out. For the block diagram, so that is the three inputs, A, B, and borrow in, and the output is difference and B out. So the application of the full subtractor is to subtract larger binary numbers, and it is generally employed in arithmetic logic unit. The fifth is the multiplexer. Let's say we have a 4 by 1 multiplexer, and it will look like this, where we have 4 inputs, input 1, 2, 3, and 4. And also, there are switches like S1 and S2. So by using these switches, we can select which output we will desire from these 4 inputs. So let's say the input of the two switches is 0 and the desired output is our input 1. The same with other combinations, the desired output will be the other inputs. So this multiplexer is used in data selector such as varying audio and video in telephone network. In the multiplexer, it is the same with the multiplexer where we can select a type of data or the type of output where the input is only one and the output we have is 4 outputs. Let's use this as all. The application of the multiplexer is also in data transmission, where it is used in receiving the data from a multiplexer at the receiving end.